Hi guys, I want to talk today about how we solve these one-dimensional problems. Now, these problem-solving skills are similar in every problem that we have all year. So you're going to see Mr. Dooley and myself do this type of thing and show you how we solve these things. And I really recommend getting a step-by-step procedure of doing that. So let's talk about this, and I'll give you an example of how we would do that. As you can see on my iPad, I have 4 steps kind of with like intermediate type things. So you want to read the problem and identify the variables as you read the problem. So I usually use a highlighter or underline stuff or just label numbers that I'm given in a problem. Sometimes numbers are not part of the problem. So you have to be able to filter out what is necessary to solve with what you're looking for and what's not. You want to list the 5 variables. Our 5 variables are delta x, which is our displacement, that's measured in meters generally, initial velocity, which is measured in meters per second, final velocity, also measured in meters per second, acceleration, measured in meters per second, and time, measured in seconds. Those are our base units. So if something's given to us in miles per hour or kilometers per hour or hours or different units, we have to convert those to our base units, especially because our acceleration is generally meters per second. So that's what we have to kind of make sure that that agrees unit-wise. So as you read the problem, you have to identify what variables you know and what variables you don't. And then you have to figure out, what am I looking for? What am I asked to solve for? Now, there are 5 variables. You will always get 3. There will never be a situation where you have less than 3 that you have to go, well, I don't have a formula for that, because we don't. We have formulas that have 4 of the 5 variables, and we use those 4 to get 1 unknown and 3 known. And so as we read the situations, that's helpful. Now, sometimes it might be helpful to make a diagram. You'll find that we do a diagram a lot of the time, especially in 2-dimensional motion, but sometimes 1-dimensional motion is helpful as well. So diagramming it out might help us understand what are we looking for in that case as well. So then you have to choose an equation that works to solve for what you're looking for. Now we have 4 equations right here, and each equation has a different thing that it is solving for. Now, you don't have to use this equation to solve for delta x. You can rearrange it to solve for VF or delta t or VI and so on. But notice this one doesn't have acceleration. So if you have a situation where you know what the acceleration is, or if you have a situation where you're asked to find acceleration, that is not going to work for you. All right. The second one here does not have displacement. So if you're asked for how far is it gone, that's not going to work. Or if you're given a displacement, that's not going to work. This third one does not have final velocity, and the fourth one doesn't have time. So each one has a little bit different setup, and I neglected to put the delta t in this one here. There we go. So notice the one thing that we need in all of them, or the one thing that we could use to solve in all of them, is initial velocity. So initial velocity is in each of these. So you need that, or else you're going to be solving for it. Okay. Once you have the equation selected, now here's the thing. All of these equations work for solving any type of motion situation, but so there's not a wrong equation, but there's a better or worse equation. The better equation is going to be a 1-step process to solve something. The worst equation is going to be, I got to solve for that and then use that answer to solve for it again. All right. So then once you've figure out the equation you want to use, you want to insert the variables in the right spots and solve for what you're looking for. And then as an answer, you want to round to the correct precision and label with the correct units. I always recommend writing down the formula that you use, regardless of whether you put the numbers in right away or not. So if you have a test question that is worth 3 points, usually that 3 points is 1 point per formula. just writing it like these, 1 point for your work, which is as simple as putting in the numbers in the formula in the right spots, and 1 point for your answer. So it depends on how we grade stuff. Sometimes we'll be looking for that. So that's a good way to communicate. So let's take a look at this problem. We got a skydiver falling at 52.5 meters per second. So I'm going to write down the variables, delta x, vi, vf, acceleration, and time. And the 52 meters per second, that's a velocity, so we got to figure out whether it's initial or final. She deploys her chute, the chute opens up and slows her down to a much more manageable 6.71 meters per second, another velocity. So in this case, the 52.5 meters per second is initial velocity, and the 6.71 meters per second is final velocity. All right. We're told the rate of acceleration then at a rate of -6 meters per second. And we want to know how far she falls. So we are looking for delta x. So we don't know the time, we don't know how long it took. So we are going to choose a formula that doesn't involve time. So if I look at this bottom one doesn't involve time. So I'm going to use that formula. I'm solving for delta x, so it's not set up to solve for delta x, so I'll have to do some algebra to rearrange it, but that's well within my capability. So I'm going to put that in there. VF final equals VI squared plus 2a delta x. Now, depends on what you do. I like to solve this algebraically before I put numbers in. Sometimes it's easier after you put numbers in. But if I solve this algebraically, and you don't need to show every step, but delta x would be VF squared minus VI squared over 2a. So I know final velocity, initial velocity, and acceleration. So now I can plug my numbers in. So final velocity is 6.71 meters per second. I square that. Minus 52.5 meters per second. Square that. Very common mistake is people forget to square things. Over -6.00 meters per second squared. So now when I pull out my calculator, 6.71 squared minus 52.5 squared, I get delta x equals -2711 meters squared per second squared over -6 meters per second squared. Notice that will mean that my displacement is positive, and I get 451.871 meters. The second squared cancels out. The meter squared cancels with one of those. So I get meters. That tells me that I'm on the right track. So the skydiver travels 452 meters because that is how many sig figs we have in our measured values, 3. All right. We could do the same thing to find time, but if we wanted to find time without delta x, we'd have to use this one. So we could know how long it took her to fall that far, or how long it took her to fall and change those speeds. Since we now know the displacement, we could use this one to solve for time, or this one to solve for time. Now, I'd avoid this one generally if I have an initial velocity because you end up with a quadratic. But all of them now work to solve for the other variable that I don't know. All right, that's what I want to talk about today. So happy problem solving.